Alrighty, welcome back to another installment of Mr. Ralph Teaches You Something. Um, Today we're going to be talking about the concept of work. You're going to see me do a couple of different things today that are a little bit new for me, so just bear with me as I try to figure out how to make this thing work. Alright, I'm going to go ahead and pop up a nice little PowerPoint presentation here that we're going to work from. So, let me make sure. Overlays. Oh, no, I don't want that yet. Oh, God. You see what I'm talking about? I don't know how to work this thing. All right, so starting out today, we have the essential question, basically, what is work? Well, work is it occurs when a force, that is to say, a push or a pull causes an object to move some distance. Those two things are very important. So you can see where it says force and distance, and they're bolded. Okay, so let's put that into practice, and let's look at a couple of different situations in work could be being done or it could not be being done. All right, so here we have a situation in which we are looking at two guys pushing a car. Now, there are a couple of things to take note of. First off, if we're talking about these two gentlemen pushing this car, we will assume that the car is somehow moving in this direction, and that these two gentlemen are exerting some sort of force in this direction. Well, we've got the two components that we need when we're talking about work. We have force, and we have some sort of distance that's being traveled. That, to me, sounds like work is indeed being done. The only situation in which work might not be being done is if, say, for example, instead, these two guys are not actually making any headway and this car is not moving for some reason. Maybe it's got a flat tire, maybe there's just too much friction to overcome, and as a result they're pushing and it's just not moving. All right, another situation we might look at that's a little bit less common would be people playing tug of war. So again, this is kind of a, hey, it depends on the situation type thing. In the case of these people, if they're in a dead stalemate, no work is being done because they may be exerting forces on either side, but if no distance is covered, then no work can be done. However, as soon as one team starts to move the other team forward, say for example, they're exerting a force in this direction and the people are all moving in this direction, they are doing positive work, and the people on this side that are getting pulled in this direction but exerting a force in the opposite direction, they are doing negative work. So the question was, if they're in a stalemate, well, no. If they're in a stalemate, no work is being done. Is work being done in this particular instance? Well, obviously this gentleman is exerting a force, but logically there's no real reason we would see that this wall would suddenly push over. He's not a superhero. And so as a result, there's a force, but there's no distance that's being covered by the object that's being pushed on. So I'm going to say that work is not being done in this situation. Here we have someone that's picking up a box, so they're exerting a force upwards, and that box is moving from this point to this point. So it looks to me like work is being done because we've got a distance that's being covered and a force that's being exerted. So yeah, I'm going to say that work is definitely being done in this case. Now, if that person was just holding the box, like in this last frame, no work is being done here in this last frame because that box, even though they're exerting a force, that box is not moving. So just keep that in mind. Here's another interesting situation to think about. Is work being done by a hovering helicopter? Well, if we consider the whole helicopter as a system, we would talk about maybe it's exerting a force against the force of gravity that's pulling it down. So it has to exert a force upwards to stay hovering. However, if it's hovering, we understand that its velocity is zero. So that means it's not accelerating. It's not changing its distance at all. Doesn't seem like it would be covering any distance if that's the case, if it's hovering. So that means that we have the force component, but we don't have the distance component. If we just look at the body of the helicopter, no work is being done. I think most of you would look at this situation and say, well, work has to be being done because otherwise the helicopter would fall out of the air. And I agree. Work is being done in some fashion, but the whole system is not doing work. If we look specifically, say, for example, at the rotors here, they are moving very quickly. They're covering a large amount of distance very quickly. And they are the ones that are exerting the force downwards. So yes, actually the rotor, just the rotor, is doing work because it's moving, it's covering distance, and it's exerting a force in some fashion downwards. So work is being done in that case. You look at these gentlemen that are jumping out of the helicopter. Of course, if they started up here, they're going down here. The force of gravity is pulling them down. So work is also being done on them because they're moving a distance and a force is being applied to them. In this case, it's gravity. And then finally, we have a couple of different situations. Here we have the asteroid Mau Mau, which was an asteroid that actually originated from outside of our own solar system. Came racing through, and we saw it pass by the sun just as it was leaving. Some people speculated that it was actually an extraterrestrial craft, but this is our best guess as to what it looked like, long and thin. So as it came through our solar system, it probably wasn't moving at constant velocity. Once it leaves our solar system, or left our solar system, it was moving at pretty much a constant velocity. Well, if we're moving at a constant velocity, we are covering a distance. But if we're not accelerating, is there a force? Moving at constant velocity means that net forces are zero. And anytime net forces are zero, then no, work is not being done. So in this case, no work is being done on this object even though it's moving at constant velocity. So it is moving over a distance, but no force. Here we have a weightlifter. Again, this is one of those situations in which we could have multiple things happening in the picture. We don't really know. It's not a video. So if she's holding this weight over her head, then no work is being done because these objects are not moving, even though she's exerting a very large amount of force. She's not changing the distance the object is from the ground or wherever. However, if she were picking it up or putting it down, doesn't matter. Whichever direction, work is being done. And then finally, I have this image of these ladies carrying jugs. So here we see an interesting case. She is holding a jug up against the force of gravity, so she's exerting a force up, and she's moving in this direction. So if I were to redo my overlay here, you can't see what I'm doing, but I can see what I'm doing. I'm going to go ahead and hit my overlay key so we can draw a couple of things on here. And what I want you to see is that if we talk about her, what's actually happening is she's exerting, did it again with this opacity thing that it likes to do. I'm wondering how that happens. Anyway, you don't need to know about that. She's exerting a force upwards, okay, like this. So the force is upwards, but the distance that she's traveling is perpendicular to that force, and you can see that here. That means that no work is being done. So work is zero in this case, which is an interesting case. Force is applied vertically, distance is done horizontally. So it can't just be that a distance and a force always result in work. There have to be some other components in our understanding as to where work actually comes from and what it actually means. So let's look at that. Okay. Here are the relationships that we need to understand. First off, for work to be done, a distance must be traveled. We've kind of shown that through our examples in this particular PowerPoint so far. For work to be done, force must also be exerted. Can't have work without a distance covered and a force be exerted in some fashion. Finally, and most importantly, work and force must be in the same axis, or at least a component of that force has to be in the same axis of travel. That's why when we look at this one, the component of the force was completely perpendicular to the distance that she was traveling, and so no work was being done because it's not in the same axis. We got an X and a Y axis, right? So here's a handy dandy little chart that you might want to put in your back pocket or write down, maybe pause the video and put somewhere, so you kind of understand how forces and displacements or distance covered are related to work. Well, the first one is what we just talked about. If we have a force and a displacement and they are perpendicular to each other in some fashion, then no work is being done. Okay? Force in one direction, displacement 90 degrees off of it, no work is being done. Work is zero when the force is applied perpendicular in that displacement. However, when we have a force in the same direction as our displacement, the work done is positive. Okay, so think about that for a second. Force is a vector, which means it has direction. It can be a positive or a negative. Displacement is also a vector. It can be positive or negative. So if both work and displacement are either positive or negative, doesn't really matter. When we multiply them together, we're going to get a positive answer. Likewise, if we have force moving opposite the displacement, it doesn't matter which side of this is negative and which side is positive. We're going to find that when we multiply these two things together, the work done is negative. Now you just heard me say multiply these two together, so I'm kind of tipping my hat as to what the formula for work actually is. So let's just go ahead and look at that. Here is your formula. Work is equal to the force times the distance. I just went over what part of that formula is scalar and what part is vector. Well, we would talk about distance being a scalar. I don't really like it. I'd prefer that this would be called displacement instead of distance because it would make this work out so much better. But just understand that going back to this, if we talk about instead of displacement, if we talk about distance, when force is the opposite direction of the displacement, we're going to have a negative work done. If it's in the same direction as our displacement, then work is positive. Let me give you an example to kind of understand that a little bit better. Let's go back here. Okay, so in this case, she's picking up this box, or maybe a he, I don't know. She's picking up this box with some force, and the box is moving upwards in the same direction as the force. In that case, the work is going to be positive because both of those two things are aligned in the same axis. So as she picks up the box, she's doing positive work. However, I want you to envision a situation in which maybe instead of picking up the box, she's trying to set a very heavy box back down to the ground, or pulling it off of something and laying it down on the ground. That still takes effort, it still requires a force, and there's still a distance that's being covered. However, as she's setting that object down, she's exerting a force upwards, but the object is moving downwards. And so as a result, she's now doing negative work. She's resisting the work that gravity wants to do on the object. Because if she weren't there and this box was here in midair, the box would have work done on it by gravity. It would literally fall to the ground, do that force, changing its distance, so positive work is going to be done by gravity in that case. Well, she's coming along and she's saying, no, I'm going to resist the work that gravity wants to do by doing my own negative work in this direction, letting the object go down slowly. So negative work is very interesting because what it does is it actually steals something from a system. We'll talk about that later, but it's actually stealing energy from a system. Think about a car braking, for example. A car braking is stealing energy or momentum from the system that's never going to return. It's not like if you go up a hill. When you go up a hill, your force and your distance are aligned in the same direction. And so as a result, when you get to the top of the hill, that force and that comes back out as you go down the hill, and you get that positive work back out. However, when we brake, force and displacement are in opposite directions. That's just gone. We don't get that work back out somehow. It's just, it has left the system. So again, our formula for work is work equals force times distance. We know that force is newtons and that distance is in meters. So we would expect this to be Newton meters, and some people in some places will call it Newton meters. But for work, the variable W is going to be equal to joules. We're going to talk about work in terms of the unit, joules. So just keep that in mind. I'm going to end this video here. We're going to progress forward by talking about a different example in the next. But just understand, our formula for work is work equals force times distance. The unit for that is typically joules. We don't call it Newton meters or something else. And this is actually named after a gentleman, somebody Joule. I don't remember his name off the top of my head, unfortunately. All right, I'll see you again in the next video.